Now that we have discussed about solving this question in two different ways, right, using m1x1 and m1a1, now let us spend some time understanding the significance of this word uniform, and then let's spend some more time in understanding the calculation of these individual center of masses and then combining them together. Okay, so first up is understanding the concept of uniform section. See, the term uniform section is crucial in solving the center of mass problem. Why? Because uniformity in a section of solid means equal mass distribution. A uniform metal plate means that its mass is evenly distributed over its entire area. This will allow us to treat the center of mass as the geometric center of each section without worrying about the variations in mass density. I do understand that things are not clear here. It may take some detailed time to understand this concept. Okay. So, in a uniform plate, the mass density, which is mass per unit area, is constant throughout. This means that if you take any two sections of the plate with the same area, they will have the same mass, which basically translates to this. If sigma 1 is equal to m1 by a1 and sigma 2 is equal to m2 by a2, and then if we say that the uniform that the mass density is constant throughout, it means sigma 1 should be equal to sigma 2, and therefore m1 by a1 should be equal to m2 by a2, or in other words m1 a2 should be equal to m2 a1. And in this, if a2 is equal to a1, a2 is equal to a1, then it should imply that m1 is equal to m2. Therefore, when sigma is a constant and when areas under consideration are equal, we can say that the corresponding masses should also be equal. M1 is equal to M2. Okay, right. Now, because the mass is evenly distributed, the center of mass of the plate coincides with its geometric center. Now, when we say geometric center, this applies only to regular figures. So, most of the questions that we see here will be focused on regular figures. This simplifies calculations because you don't need to account for variations in mass density. Now, for geometric center, we always consider simple symmetric figures like rectangle, circle, or triangles. Okay, and why actually the reason why we consider these figures are because it is easy to consider, it is easy to determine their geometric centers. Okay, for say for instance for rectangles it will be the intersection of diagonals, for circle of course the center, so on and so forth. Okay, now this geometric center will also be the center of mass when the plate is uniform in nature. Okay, so that was regarding the concept of uniform plate. Sorry, yeah, uniform plate and geometric center. Now, how do we apply these two in finding out the center of mass of the overall body? See, for that we use the composite body method. Now, what is composite body method? It implies that the body under consideration can be considered to be a composition of multiple individual bodies. For instance, this complete figure solid lamina given here can be considered as one large base rectangle, one rectangle on the top and the other on the right. So we have large base rectangle, left rectangle, and a right rectangle. Okay, and by using the additive and subtractive method, which means adding or subtracting these sections, we can determine the overall center of mass. How? Let's try to understand that aspect as well. So we have x bar is equal to m1 x1 plus m2 x2 plus m3 x3 the whole upon m1 plus m2 plus m3, right? So this is what we have as the given figure. So we can write this as m1 as sigma 1 a1 M2 as sigma 2 A2 and M3 as sigma 3 A3. We already have discussed this part, right? And if all these sigma 1, sigma 2, sigma 3 are representing uniform density, then sigma 1, sigma 2, sigma 3 should be equal to some sigma, some random, say some sigma, say sigma 1 is equal to sigma 2 is equal to sigma 3 is equal to sigma. Okay, in which case these sigmas from the numerator and from the denominator can be cancelled, and what we get is a1 x1 plus a2 x2 plus a3 x3 by a1 plus a2 plus a3. And what is x bar and y bar? X bar and y bar determined in this manner will be the center of coordinates of center of mass. Okay, so that's how we use the composite body method. Now, all of this is clear, but what comes to our mind is what would be different if the question would have said non-uniform? When that's why we consider the questions at the JEE advanced level and some of them at the JEE mains level as well. Now, if the metal plate had varying thickness or density, we would not be able to assume the geometric center as the center of mass. See, that's where the significance of geometric center comes into picture. So, if the plate is of uniform density, the geometric center would coincide with the center of mass. But if the given plate is not of uniform density, we would need integration or even more complex weight-based calculations to determine the exact center of mass. As in this figure, where if you see, the center of mass is not equal to the geometric center because there is no uniform distribution. Why? Because what I was trying to represent here is, say, okay, I think it won't be clear from this diagram. Maybe that will be clear from the next diagram. Let's try to. Okay, I'll come to the diagram in a while. Now, if you have to consider the differences between uniform section and non-uniform section, we discussed right now that the center of mass would coincide with the geometric center when the given lamina under consideration has a uniform section, and it may not coincide with the geometric center when the given lamina is of varying thickness or of non-uniform thickness. Okay, so I hope this concept is clear, the significance of geometric center. Now, we need to understand and appreciate another concept here. And why are we doing this in this detail? Like I said in the previous solution, we are also aiming for assertion and reasoning questions, which will test your not just your numerical skills but also your conceptual skills. One of which in this particular section is the concept of mass distribution being evenly and unevenly distributed. What does that mean? We will now focus our complete discussion on evenly and unevenly distributed mass. Let's see how. Now, if we have a uniform rectangular plate, which means here the mass is distributed evenly, right? And let us assume that the width of the rectangular plate is 4 and the height of the rectangular plate is 2 meters, and the weight being 8 kilograms. Okay. In this case, what is the total area? The total area here is width into height, which is 4 into 2 equal to 8 meters square. Right? Now, what is the mass density here? The mass density here is mass per unit area, sigma. What is the total mass? It is 8 kilogram. What is the total area? It is 8 meters square, which means the mass density here is 1 kilogram per 1 meter square or per meter square, which means every meter square area of this plate will weigh 1 kilogram. Or in other words, no part of the plate is neither heavier nor lighter than any other part of the same plate of the same size. Okay, let's revisit that one more time. No part of the plate is heavier or lighter than any other part of the same size. Okay, now If you understood this part, which is no part of the plate is heavier or lighter than any other part of the same size, try to think, is this figure combination correct with respect to, or is it possible to say that this figure represents an mass density of 1 kilogram per meter square when the rectangle is of 4 by 2 size? Will it be? No. Why? Because as we said, if we consider this to be, okay, the diagram here also becomes a bit confusing, right? Oh, my bad. I should have opted for a proper rectangle. Okay, so what I was trying to convey here is, if this is 1 kilogram meter per meter square, this will be 1 plus 1 plus 1 plus 1, which will give you only 6 kilograms. But the total weight here is 8 kilogram. So such a distinction is, such a division of mass is not possible here. But if we choose this reference, right, if we choose this reference, then it makes sense. Why? Because this is 1, this is 1, this complete width is 4, which is divided by divisions of 1 meter length. And now 1 meter square, which means this area, 1 meter square will contain 1 kilogram. So this will be 1 kilogram. This also 1 kilogram. These as well. And now if we add these 1 plus 1 plus 1 plus 1 4 times, 8 times, what we get is 8 kilograms. Therefore, such a division makes sense here. Okay. So this is how we divide the given laminas based on what? Based on the mass distribution. Okay. Once we find out the mass distribution, then we can find out the center of mass, which in this case will be the point of intersection of the rectangles, right? Now, for a 4 by 2 rectangle, the x coordinate of this rectangle would be width by 2, which means if I assume this much to be the width, right, then the coordinate here, center of mass coordinate over here, will have both x and y. Let us call that as x bar and y bar. X bar and y bar. So the x bar will be equal to width by 2 and y bar will be equal to height by 2. Okay. So if this was width is equal to 4 and height is equal to 2, then the coordinate here for center of mass would be width by 2, which is 4 by 2, 2, and height by 2, which is 2 by 2, equal to 1, 2 comma 1. Okay, I hope that makes sense. Or maybe like this. Okay, so the coordinate of which means it is this distance here represents distance from the x-axis and this represents distance from the y-axis, right? So you walk 2 units to the, sorry, if you walk 2 units along the width, and then from there if you walk 1 unit along the height, that point is where the center of mass is located. Okay. Now, what would be the case if this was the same for a, if we were to discuss about a non-uniform rectangle? See, if we were to discuss about a non-uniform rectangle, then we know that the 1 kilogram per meter square density distribution would not be the same, which means some of the area may have 1 kilogram per meter square and some of the other portions may have 3 kilogram per meter square, or some of them may have 1 kilogram per meter square and other having 0.5 or even less than that. Okay, which would make either of the sides go more heavier or more denser. So maybe the left hand side or the right hand side is more denser or more lighter. That depends upon the distribution. And what will happen in such a case? That is the point here. That is where we expect a potential, assertion using question. Well, not at the simple level, but of course at the a slightly higher level. Now, if the center of mass, sorry, if the weight distribution is not uniform, then the center of mass will shift towards that side which is more denser. This is because more mass is concentrated on that side, pulling the balance point towards it. So if we were to analyze like this, so if this was the center this was the center of mass initial, and if we center of mass initial, in which I mean center of mass with even distribution of mass. But in the second case, if you consider that one side of the lamina is unevenly distributed, then we can say that this center of mass of even distribution will incline towards, which means we'll have somewhere over here the center of mass of uneven distribution. The center of mass will shift towards the denser side. Center of mass will shift towards the denser side. Okay, so just to compare the differences between the center of mass of a uniform versus a non-uniform rectangular plate, mass distribution is even in uniform, is uneven in non-uniform. Center of mass would be at the geometric center for uniform, and it would be shifted towards the denser region in a uneven distribution. Okay, right. Now, if we were to compare the center of mass of a uniform versus non-uniform rectangular plate, this is where we draw the diagram earlier. So if this was the center of mass of a even plate, right? Center of mass of even plate, then for uneven distribution, it would shift towards the side where there is more mass density. So this is center of mass of even, and this represents center of mass of uneven distribution, which has shifted by this length over here, Okay, I hope that makes sense. Okay, so okay, wait. I was about to discuss something else here. My bad. Please give me a second. To summarize, my bad. To summarize this, if we compare the mass distribution in uniform and non-uniform plate, in a uniform plate, the mass distribution would be common across equal areas, right? So this will make 1 plus 1 plus 1 plus 4 into 2 becomes 8. Whereas in non-uniform rectangular plate, there will be uneven distribution, more mass will be concentration on one side. So say this might be 3, this might be 2, this might be say 1, 3 plus 1, 6, maybe 1, and then we only have very little mass here, 0.5 plus 0.5. Okay, but in either case, 3 plus 1, 4, plus 2, 6, plus 1, 7 and 8, the mass may remain the same. The overall mass may remain the same, but the distribution would be different. I hope this gives you better clarity on the idea here. Now let's see the difference between the center of mass considered to be the geometric center, which was something that I tried to do in the previous section. So if this was the center of mass of even distribution, we know that it will shift towards the denser region, maybe somewhere around here. This will be the center of mass of uneven mass distribution. And if you compare these two, this point where the center of mass of even distribution was present, it means that it has shifted towards the region where there is more mass density. Now, what was the mass density? We earlier said that this was 1, 1, 1, and here it was 3 and 2 and 1 and 1. So the the center of mass has shifted towards that region where there is more mass present. Okay, so yes, so that's the concept behind center of mass dependent on uniform thickness of the plate. Okay. So yes, now let us try to emphasize more on the numerical part to find out the center of mass of individual figures, and then how to find out the center of mass of individual figures with respect to a origin.